Okay, let's start. Welcome to today's ICON seminar. And today we have Professor Ruqi Zhang giving us a talk about her research on discovering and controlling AI safety risks in foundation models, the probabilities perspective. And Dr. Ruqi Zhang's work is very timely, and I hope we will learn a lot of useful lessons from this talk. And just a brief bio for Dr. Ruqi Zhang. She's an assistant professor in the Department of Computer Science at Purdue. Her research focuses on probabilistic machine learning, generative modeling, and trustworthy AI. Before joining Purdue, Dr. Ruqi Zhang was a postdoc researcher at the Institute for Foundations of Machine Learning at the UT Austin. She received her PhD degree at Cornell, and she has been a key organizer of the symposium on probabilistic machine learning. She has served as an area chair for various conferences such as ICML, Europe's ICLR, so on and so forth. And the contributions have been recognized by various awards such as AAAI, New Faculty Highlights, Amazon Robotics, Amazon Research Award, Spotlight Rising Star in Data Science, Seed for Success A1 Award, and Rosling Research Scholar. With that, let's welcome Dr. Ruqi.
Thank you everyone for being here, and thanks for having me. I'm Ruqi Zhang, and I'm assistant professor in the CS department at Purdue. I joined ICON as affiliated faculty, I think 1 year ago, and today I'm super excited to share some of our recent work on AI safety in foundation models, especially how to discover and control safety risks from a probabilistic perspective. As we all agree, I guess foundation models are like super powerful. To put in context by foundation models, what I mean include large language models such as ChatGPT, Cloud, Gemini, and also multimodal models, especially vision language models are quite well developed nowadays. Like all the ChatGPT, Cloud, Gemini all have their vision language models version because you can not only input text but also image to the models. Besides those closed source models, there are several popular open source models like Queenwing, Lava, InterVL. Building on the foundation models, a wide range of applications have emerged. Okay, I think it's fair to say that foundation models represents the most intelligent systems that we are ever able to build, and they create a substantial values in science, economy, and society. However, foundation models are far from being trustworthy enough to handle most of our tasks. Let me show you some concrete examples. Nowadays, like many companies are using AI chatbot to handle like customer queries. In this case, Air Canada's AI chatbot provided incorrect refund information. Okay, and this results in legal and financial liability. In the end, Air Canada lost the court case and paid the customer damage and court fees. Okay. Another example is in healthcare. Okay, so in this case, the client expressed a feeling of loneliness and depression. However, the response from LM is considered unethical. Okay, so it reinforced the rejection and abandoned feeling. And this is considered to be unacceptable in a real-world setting. And for like a human counselor, this is definitely not allowed to give such response. The safety issues are not limited to large language models. Vision language models can also give like unsafe responses. In this example, the input image and the text involve some harmful concepts, such as weapon and property crime. In the first case, all of the three VLMs gave harmful responses. And in the second case, two of the three VLMs gave unsafe responses. And the risks become even more severe when we apply foundation models to physical worlds. Okay. In this case, the study has 3 different robots. Okay. And they test the robots across a wide range of safety scenarios, such as bus collision, ignore stop sign, weapon search, so on and so forth. Okay, so a lot of different safety scenarios. And actually, the robots are highly vulnerable to harmful instructions. So the number in red represents attack success rate. So basically, how likely we can make the robots conduct harmful physical actions. So you can see that in almost all cases, the attack success rate is 100%. Okay, which means it's very easy actually to make robots to do something harmful in real world setting. Okay, so foundation models are powerful, but they are still quite brittle, and they are not reliable and trustworthy enough to be deployed in real world settings. Then what should we do? Like, how can we make them more reliable and safer? Well, traditionally, what people do is to try to find all possible specific questions or test cases where the model gonna behave unsafely, right? So once we identify those cases, then we can fix those behaviors. In this plot, like each red dot represents one individual failure case. Okay, so then our goal is to find all possible such red dots in the space. Okay, well, this can be useful, but it treats failures as like individual points. It does not explain, right, where these failures come from and how they are related, and also how likely they will occur in like real world settings. Moreover, this approach is obviously not scalable, right? The search space is just too large. It's just impossible to find all possible edge cases. In contrast, we propose a probabilistic risk perspective. Okay, so we believe that each failure shouldn't be treated as individual points. Okay, because they really indicate a broader class of region where models are likely to behave unsafely. Okay, for example, the Air Canada's AI chatbot is likely to not only fail on that specific refund question, right? It's more likely gonna fail on a broader class of refund policy related questions. So therefore, we believe that the safety failures should be characterized as distribution, and not just the isolated ones. So in this plot, we characterize the risk distribution over the entire model behavior space. And here, each peak represents the regions where the model is likely to behave unsafely. Okay, and we could have like multiple modes, and each mode is corresponding to a different type of risk. Okay. And from this perspective, we naturally have 2 fundamental questions need to be answered. The first one is discovery, right? Like, how can we discover and characterize the risk distributions? Like, how can we know like in which region the model will behave like unsafely? The second question is control, which means how can we ensure that the model will always output a safe contents? It will always behave safely. Or in other words, we want the behavior to be restricted to the safe region. In today's talk, I will answer both questions. In the first part, I will introduce probabilistic red teaming for discovering risk distributions. And in the second part, I will introduce inference time alignment for controlling model behavior. All right, then let's start the first part. So here, our goal is to discover safety risks. Okay. Technically, this is called red teaming. Okay, we want to discover inputs that cause the model to behave unsafely. Okay. And this is a challenging task because again, the input space is just so huge, right? So consider a large language models, the input can be any text. If for a visual language model, the input can be any text plus any image. The input space is just like so large in order to do extensive search. Also, failures are rare, right? Like most of the time, the model will behave just okay, right? It will behave safely. Only a small amount of time, it will behave like harmfully, and the failure cases are essentially edge cases. And finally, to do red teaming, like typically, we're gonna heavily rely on expert knowledge, right? We need human experts to handcraft test cases in order to stress testing, in order to stress test model behavior. And those handcrafted crafted test cases require a lot of labor, human effort, and is also incomplete. Based on the probabilistic perspective that we mentioned at the beginning, we want to address all those challenges. Okay. To be more concrete, okay, so the risk distribution we want to characterize here is the following. Okay, we want to model the distribution of input X, okay, given a harmful behavior Y. Okay, so this is the distribution that we want to characterize. And by base rule, we know that this distribution is proportional to the probability of the harmful output given the input, and then times the prior distribution of the input X. Okay. So this is different from traditional red teaming in the way that in traditional red teaming, given a target harmful output Y, it will only find one single input X that induce that target harmful behavior. And here instead, we try to modify, or we try to characterize the entire distribution of X that can all induce the harmful behavior. After this formulation, then like characterizing the risk distribution is equivalent to estimating the posterior of the unsafe input given the harmful output, right? So this is a problem of posterior estimation. So since this is like kind of a standard setup for posterior inference, we can use some existing approaches. Here we propose to use variational inference. Okay, so we can use the variational inference approach to estimate the posterior of unsafe inputs given the harmful outputs. Okay, so this is the core idea of probabilistic red teaming. Okay, so like instead of just finding one specific question that induced the harmful output, we are aiming to find the entire distribution of the harmful inputs. We apply this idea to large language models, okay, and we call our method Vera. So this is the overall pipeline of probabilistic red teaming for LLMs. Let me walk you through this pipeline step by step. At the beginning, okay, we have a target harmful behavior. Okay, we want to induce. Okay, we will input this harmful behavior to attacker LM. Okay, so this is another LM. Okay, which we will use to generate harmful inputs. So we will tell the attacker that this is the target behavior that we want to induce, and the attacker model will output a set of possible inputs that can induce this target harmful behavior. Okay, and then we're gonna fit this set of inputs to the target LM. Okay, so the target LM is the model that we aim to jailbreak. Here we assume minimum access to the target LM. Okay, we assume it's black box, which means we can only access the outputs of the models. We do not assume the access to like model weights or model lodges. Okay, we only assume the outputs access. And then, right, the target LM will output the responses to the set of inputs. Okay, we will use a judge model. So the judge can be either human experts or another LMs. So here in the paper, we use another LM as the judge to evaluate whether the output is considered harmful or not. Okay, so it will give us a judge score to tell us whether this is a successful jailbreaking or not. At this point, we already have all the information we need to compute our objective function. Okay, so the objective function is allowable. Okay, so this is evidence lower bound. This is like the common objective function that people use in variational inference. Basically, the allowable contains 3 terms. The first term is the prior term. So this term is easy to compute. It's just our prior knowledge about inputs. The second term is a posterior term. This is basically how likely the attacker gonna generate this specific input. Okay, and the third part is the most important part. Is the likelihood term, which estimates the probability of the harmful behavior given the specific input. Okay, and this term will be evaluated based on the judge score. Okay, and once we compute the variational objective, we can update our attacker model based on the value of objective. Okay, the way that we update model is using reinforced estimator. This is because when you take the gradient of the objective with respect to the attacker parameter, okay, you need to use reinforced estimator to avoid computing the gradient through the target LM, because we only have black box access to the LM. Using reinforced estimator, we do not need to compute the gradient back propagate through the target LM. We only need to compute the gradient in terms of our attacker LM, which like we can control because that's our model. And effectively, after this reinforced gradient update, the attacker gonna increase the probability of generating X with high objective value, and it will also decrease the probability of generating X with low objective values. Okay. Overall, okay, the high-level idea is actually similar to reinforced learning. If you are familiar with RL, basically we have an attacker LM, and the attacker LM gonna generate a bunch of candidates jailbreaking inputs, and then we're gonna use the judge model to evaluate how good those inputs are, and then we're gonna give this feedback to the attacker LM. Okay, so like some of the inputs are good, and some of the inputs are bad. So based on the feedback, the attacker LM can learn like what inputs it should produce in the next round. And the attacker LM essentially represents this posterior distribution. Okay, so the attacker LM is this posterior distribution. Okay, and in the end, like after training the attacker model, in the end, it will generate a bunch of diverse prompts. So essentially, you can generate infinite number of jailbreaking prompts because you already characterize the posterior distribution of the inputs. You can draw like whatever number of samples that you want. In contrast, in like traditional jailbreaking methods, you can only first it requires a template pools, requires human experts to manually construct several templates, and then given one specific harmful outputs, it can only give you one specific input. And if you need more inputs, you need to train, repeat the process all over again to get more inputs. In contrast, for our method, we can generate a bunch of prompts all up at a time. So in summary, some key advantages includes automatic search. It doesn't require extensive human inputs. It gives us distributional discovery because it can characterize the entire posterior distribution and generates a diverse safety failure process. It's also very efficient because we only need to train the model once. And then after training, we already characterize the posterior distribution and we are free to generate whatever number of samples we want. Here are some empirical results. We compare VARA on several models, including open source models, Llama, Vicuna, and also closed source models like GPT, Gemini. We compare against a lot of existing jailbreaking approaches, and we show that this is attack success rate, how likely the method gonna jailbreak this target model. Okay, so you can see that the attack success rate of our approach is actually significantly higher than existing approaches. Okay, for example, for Gemini Pro, our method achieved 48% attack success rate, whereas existing method achieved 18%, 12%. So. We also test transferability, efficiency, diversity of prompts, and how the performance of our approach against common defense approaches. You can find those results in the paper as well. So we are excited to buy the results we obtained. And then we are thinking if it's possible to apply the idea to other type of models. So in the next step, we test this idea for large multimodal models. This is the multimodal red teaming is even harder because the input space becomes larger, right? So here I show some examples for red teaming visual language model, and here you have both image and also a text, right? And then you aim to induce some harmful behaviors. Okay, so the search space becomes even larger. To do probabilistic red teaming for multimodal models, the key difference, okay, is the target distribution. Now becomes a joint posterior distribution. Okay, so if we are thinking of visual language models, then the target distribution becomes a joint distribution over both text and image. Okay, so not just the text. We consider the distribution of both text input X and also image input V. Okay, we want to model this joint distribution rather than assuming that text and the image inputs are independent, because a simpler way could be you model the text distribution and you model the image distribution. But we think that the multimodality red teaming is challenging because there's a complicated interaction among those multimodal information, right? The harmful information can be encoded in many different ways, right? Depending on how you do that, based on a pair of text and image inputs. So we want to model this joint distribution. We want to capture this complicated interactions among multimodal information in order to find more possible unsafe inputs. Okay. So I won't go into too much detail here, but the most important part is at the beginning. Okay, is the output from the attacker LM. Before, the attacker LM only outputs text. Okay, but for jailbreaking vision language model, we also ask it to output an image query. Okay, and the image query gonna be fit into a diffusion model. Okay, to generate a corresponding image. Okay, the diffusion model that can be any diffusion model that take a text instruction and generate a corresponding image. Okay, and then we will combine the generated image and the text together as the input to the vision language model. Okay, so by this way we can coordinate both explicit and implicit adversarial signals. Okay, so typically the image can be used to encode implicit signals. Here are empirical results. And again, we test on open source models like QueenWing, InterVL, and also closed source models like GPT-4o. So you can see that the attack success rate is pretty high compared to existing approaches. So for example, for GPT-4o, we obtain about 67% attack success rate, whereas the best previous approach can only obtain 14% attack success rate. And we attribute this significant improvement to capturing the complicated interaction among multimodalities, and also to capturing the entire distribution of the input space. Okay, so by the way, we also consider to so what on one of our ongoing projects, we also apply this idea to jailbreaking foundation model based agents, right? Because agents is the one that capture that can complete the task from end to end, and we want to understand the safety issues there. And we already obtained like a very promising results, like the attack success rate is again like over 90%. And I'm also very interested in understanding and try to figure out whether this approach can be helpful for robotics safety. And if you are interested, or if you have any thoughts about this, I'm very happy to chat more offline. Okay, so this is for this concludes the first part where we develop a probabilistic red teaming framework to discover the risk distribution. And now I will move to the second part, which is control. So once we characterize the risk distributions, you might think we are already done, right? So once we figure out where the model is gonna behave unsafely, then we can fine-tune the model, we can train the model to make sure that the model will not output unsafe contents for those scenarios. But a key challenge is that safety cannot be fully solved during training, okay? Because the models can encounter many new inputs, new environment, new adversarial strategies. So there are many things are dynamics and adaptive during test time. And we won't be able to consider all possible cases during training. It's simply impossible. So here in this figure, during training, the risk distribution may be something like this. But then during test time, distribution could shift, and it will create unseen safety risks. Okay. And this implies that we need some mechanisms that enforce safety during generation, during deployment. Okay, no matter how the environment change during test time, we can always guarantee that the model will output something safe. Okay, so this is something important to be ensured. All right, then how can we do? What should we do to achieve that? Again, like we can solve this problem from the probabilistic perspective that I mentioned at the beginning. Okay. Concretely, we can frame the original generation distribution, right? So if we do nothing, right, the original generation distribution will be something like this. Okay, so the probability of y given x, and some outputs may be safe and some output may be unsafe. Okay. If we apply safety control, then we want to achieve this. Okay, we want to achieve a controlled generation distribution. And that means we want to shift the probability mass away from unsafe outputs, and we want to put this mass for the safe outputs. So this controlled generation distribution can be defined as the following. So this safe distribution is proportional to the original generation distribution times a constraint. Okay, a constraint term. Typically, this is this R function here is a reward function. It evaluates how safe this output is given the input X. Okay, so the higher the reward score is, the more safer the output is. Okay. So basically here, if we think about safety control from a probabilistic perspective, that means we want to remove the unsafe probability mass, okay, and keep the probability mass constrained in the safe region, okay. And then if we do that, then we define a new target distribution, which is called a controlled generation distribution. Okay, it's a new distribution that proportional to the original distribution times a constant term. Okay, if we do that, then we have a new target distribution. Okay, so this is a safety constraint output distribution. Okay. If you are familiar with reinforcement learning, okay, you may know that if you use RLHF or DPO, you can do safety alignment. Actually, this target distribution is the optimal policy under RLHF and the DPO. Okay. Then, like, if we are able to like always generate samples from this new target distribution, then we can ensure that the outputs are always safe. Here are several like benefits of this formulation. So first, there's no training. Okay, we can just directly sample from this reward shifted distribution without touching the foundation models. Without touching the original foundation models. Is flexible because the reward function, right, can be anything, right? Depending on the applications, depending on the scenarios, you can use different reward functions to satisfy different safety requirements. And also it's very adaptive because this formulation can be used as a plug and play approach. Like you can combine different foundation models with different safety requirements, okay? Because it doesn't require any training, any fine tuning. Even if you change your foundation model, like you know that the foundation models are like updated frequently nowadays. So you do not need to train your model all over again. You just need to plug in the new foundation model and the framework still works. Okay, and if we agree that that's our new target distribution, the next question is how to sample from this target distribution. Okay. This is not a trivial task because this new target distribution is intractable. We do not have a closed form expression for this target distribution. So how to sample? Here are several options. The first option is best of n. Okay, so best of n basically means that you're gonna generate n outputs from the base model, from the foundation model. And then you choose the one with the highest reward score. Okay. It's like pretty simple. Just independently generate n outputs and then choose the one with the highest reward score. So this is called best of n. This is a very popular decoding approach. However, this approach gonna waste a lot of LM calls, right? Because among the n outputs, we will only use one of them. So the majority of the outputs will be wasted. Another option is rejection sampling. Basically, that means we generate one output and then from the foundation model, and then check whether this output is safe or not. Okay, if it's safe, then we are good. If it's not safe, then we're gonna throw it away and regenerate from the foundation model. Again, this method is not efficient because once the outputs get rejected, we're gonna waste the LM costs. Here we propose a new sampling approach to sample from the target distribution. We call it CART, cascade reward sampling. Essentially, this is a segment level rejection sampling. Okay. Basically, we're gonna generate one segment at a time and then check whether the segment is safe or not. Okay. This is better than the standard rejection sampling because even if the segment gets rejected, we won't waste too many LM calls because it's just a segment. It's not a complete entire output. Okay. Once we accept this segment, we're gonna generate the next segment and so on and so forth. Okay. So this is a pretty simple pipeline. So first, it's a segment level rejection sampling. And if we do the rejection sampling at the segment level, it introduces another question, like how can we decide segmentation, right? Because LM gonna generate a token and then another token. How can we decide when to stop and then evaluate? Here we use uncertainty-based segmentation, which means that we're gonna check the uncertainty of the token. And we use basically entropy of the output distribution. And if the uncertainty is above some threshold, we're gonna stop and say that we already have a segment and we will evaluate using rejection sample. We do so because the model is typically uncertain when it will start something new. Okay, and this is to make sure that the segment is relatively semantically complete. Okay, and this is important because for the reward function, we will use existing pre-trained reward models, and those reward models are typically trained on complete responses, so they typically couldn't handle incomplete responses. Here we want to apply them to segmentation. And we want a segment to be closer to a complete a response. So that's why we wanted to have a complete semantic meaning. Okay, and here are some empirical results of CARs. We compare CARs on several safety benchmarks like helpfulness, harmfulness, RHF, adverse bench, safe RHF, and we compare it against several safety alignment approaches. So here we find that it's achieves high utility scores, which means that the outputs from our methods are safer compared to baselines. We also evaluate the efficiency in terms of both LM calls, reward model calls, and also inference time. So here you can see that the inference time is reduced significantly, actually compared to existing safety alignment approaches. And this is because we operate at the segment level. We also developed another approach called DAP, discrete autoregressive biasing. And this is for handling the safety problems where the safety requirements is considered local and structured. In cars, right, we use a reward model as the reward function. The reward model is used to evaluate like global safety. But for some cases, the safety is considered like local. So for example, if we want to avoiding like the toxic words, or we want to enforce some structural safety constraints, so those requirements is considered like local. In this case, we propose that where we're gonna operate at the token level. Okay. In order to do so, we introduce this bias term B to steer the generation towards a safe region. Okay. So basically, this bias term gonna steer the generation for each token, and to make sure that the final outputs will be considered safe. If we introduce this auxiliary variable, then the target distribution becomes this joint distribution. Okay, so joint distribution of the output y and also the bias term, bias variable b. Okay. So it's pretty much similar to the target distribution we have before. It's just that we additionally have this bias term to achieve like better trade-off between the original generation distribution and also the constraint function. Okay. So here, the way we sample from this joint distribution is using Gibbs sampling, which means we alternatively sample the distribution from the distribution of y, and then we sample the distribution from b, from the bias term. Okay, and to sample from the bias term, we use a method so-called gradient-based discrete sampling, because the bias term is also in a discrete space. Okay, so this is in the token space. So in order to like efficiently sample from this discrete token distribution, we use gradient-based discrete sampling, which is also an approach from our prior work. And then once we have the bias term, we're gonna generate the response from the foundation models as usual. But then each time we're gonna add the bias term to the logics in order to steer the generation of the foundation models. Okay, so this is basically the overall idea of that. Okay, so the difference between cars and that is where we do the intervention, where we do the control. Okay, if we do the control at the segment level, then we can use car. If we want to do the control over like the local token level, then we can use that. And they are suitable for different applications, depending on how you evaluate safety. Okay, and here are some empirical results. We test that in terms of both control, like whether, like how well the generative response satisfy the constraint, and also fluency, like because we also want the outputs to be fluent. Basically the result shows that DAB achieves like better fluency and constraint satisfaction trade-off. And it's also faster. This is actually something that we don't expect at the beginning. We find it to actually decode faster compared to previous work because it operates in the original discrete space, whereas the previous approaches often require some extended and relaxed continuous space in order to use gradient signal to do updates. And here, since we use the gradient-based discrete sampling, we do not require that relaxed continuous space. We can directly work in the original discrete space. Okay. And finally, we also consider applying this idea to visual language models. Okay. The key difference between visual language model and large language model is that VLM has this additional visual encoder that handles the visual inputs. Okay, so it takes the visual inputs. Okay, so a little bit of background knowledge. The VLM is typically obtained by fine-tuning LMs, right? We first have an LM, and then we fine-tune. We add an additional visual encoder to fine-tune the LM to be a VLM. Okay, so the visual input will be handled by the visual encoder. So the visual encoder will output so-called visual token embeddings. Okay, and the visual token embeddings will be concatenated together with the text embedding, and both of them will be fed into the LM backbone. So this is how typically VLM works. And we find that after fine-tuning the LM, right, to be a VLM, the safety of the model decreases significantly. And we identify the key issue to be the visual token embeddings, okay? Because they are continuous embeddings, and they typically act as outliers to the LM backbone. So although the LM backbone may be like safety aligned, okay, it may already, right, train on safety data to make sure that it will output something safe. But since the visual embeddings is outside, right, the typical distribution of the LM is considered as outliers, and the safety mechanisms from the LM doesn't work. Okay? It's very easy to bypass the LM safety. So this visualization shows experiment that we did to verify this hypothesis. Okay, so we try the original continuous visual token embedding, and we also discretize the token embedding into discrete, and we test like the performance of the safety mechanism on these two different token embeddings. Okay, if our hypothesis is true, then that means the continuous embedding should induce a higher attack success rate, which we indeed observe in practice. Like once you discretize the token embedding, right, which means that the embedding becomes in distribution to the LM, then the safety mechanism of the LM still works. But if you use the original token embedding, it doesn't work. Okay, it acts as the outlier to the LM safety mechanism. Based on this observation, we propose a multimodal safety evaluator. So basically, that means in the safety constraint distribution, the reward function now contains two parts. Okay, the first part is click model, which is used to evaluate the safety of the visual inputs. And the second part is again the reward model, which is used to evaluate the safety of the text. Here's the overall pipeline. Here you can see that the inputs is an unsafe text and image pair. Okay, it asks how to behave unsafely for driving. Okay, and the original VLM will output like something that's not safe. And for our pipeline, we're gonna use the multimodal safety evaluator to evaluate both the input text and the input image. And when they are considered to be unsafe, we will go to the safety alignment step. If they are considered safe, then we just output as usual. If they consider to be unsafe, then we will go through this safety alignment stage to make sure that the samples are from the safety constraint output distribution, basically. Okay, so like after these two steps, I see that the outputs become safe again. So this is why we call our method evaluating then aligning, because it contains basically two steps. We will evaluate the safety of the inputs first using the multimodal safety evaluator. And then once it's considered to be unsafe, we will again actually use this multimodal safety evaluator to sample from the safety constraint distribution. Okay. So here are some results. We test on several safety benchmarks. So here we compared, this is, I think, again, attack success rate, like or unsafe rate on like Llama and the Inter VL. So especially for the last column, okay, which is cross-modality attacks. Okay, in this scenario, we are allowed to modify both image and text, okay, to jailbreak the model. Especially in this cross-modality attacks, you can see that our model reduced the unsafe rate substantially. Like originally, the base model will have 100%, okay, unsafe rate, and after our approach, it will the unsafe rate will be around 12%. Okay. Besides this, we also evaluate helpfulness. Okay. This is because we want to make sure that the model is safe and at the same time still useful, right? We do not want a safe but not useful model. So we also evaluate whether our approach like affect the helpfulness of the model. So we see that it's actually still maintain the helpfulness of the approach of the model, and this is because we actually only apply the alignment for when the multimodal evaluator thinks the input to be unsafe. Okay, so when safe, then it will just output as usual. It will not change anything there. Okay, so to summarize, today I introduce a probabilistic framework for AI safety, and the discovery and the control are actually two sides of the same problem. Discovery allows us to categorize risk distribution to find out the regions where the model gonna behave unsafely. On the other hand, like control allows us to steer generation from unsafe regions and the constraint the outputs to be in the safe regions. Okay. And this framework can apply to both large language models and visual language models. Okay, and some takeaways. The first point is that we argue that AI safety risks should be modeled as structured distributions rather than isolated failure cases. Then we introduce a probabilistic red teaming framework that allows us to do distributional and systematic characterization of risk regions. And also we introduce inference time alignment approaches to make sure that the model will guaranteed to behave safely during deployment, or no matter how the environment changes. I think with that, thank you, and then happy to take any questions.
Yeah, any questions from the audience? Yeah.
Hi, grateful for the talk. I'm doing safety work from a cyber physical like control systems perspective. So the different take is really helpful. I have a question about your Vera flow diagram. You know, there's the joke about the guy looking for his lost wallet only where the street lamp is, because that's the only place he can see. The way you have your first large language model creating prompts that are designed to be attacking, and then you're updating or reinforcing that behavior. Does that silo you into only certain type of attacks that are being successful and not fully exploring? I mean, obviously it's a big big space, but not fully exploring the probability space?
Yeah, that's a great question. So actually the behavior also depends on how powerful the attacker model is. Like if your attacker model is very powerful, like very smart, then the generated jailbreaking prompts will also be more diverse, right? Like more like possible to be success. So yeah, that depends on the attacker model. And if we want to like prevent some kind of mode collapse, then we can intentionally like tell the model to like do not only focus on like one specific strategy, consider like alternative strategies. So this can be done by in context example or just a prompt.
Thank you for the talk. Regarding the case which distribution is, my question is, are you assuming any specific type of distribution? I'm asking because based on your equation, it seems like you're somehow making assuming Fourier shift in that case, you're assuming posterior, you're reusing your estimation of your posterior distribution. So that's why I'm curious.
So let me try to understand your question. You mean the distribution shift of the
So is it like a general type of distribution shift or case like some kind of poetic shift, concept shift, things like that?
Oh, I see. So actually we don't have like such assumption. Because as long as, so basically the assumption we have there is that the reward function can accurately evaluate whether this output is safe or not. That's the only assumption we have. So as long as the reward model can give us like accurate evaluation, then we can always guarantee the outputs will be safe. Yeah, but it's possible that under some weird scenarios, the reward function that we have will be able to evaluate that accurately. Then it's possible. Yeah, then that will work.
Along similar notes, you did mention that it's sort of training free, right? But if we have to train a good reward model, or all of this under the assumption that there is an auditable reward model?
Yeah, that's a great question. So in the first approach in cards, we assume that reward models already exist. Like we basically just use existing like open source reward models. Like basically if you search online, you'll find many like open source reward models that people already trained. We just use off-the-shelf models to evaluate safety. So that seems to work well. And in the second paper that depending on the tasks, like sometimes you can just like for the like keywords constant, you can have a hand-coded function to check whether those keyword is in the output or not. Yeah. So, but yeah, that's a great question. Like we do require appropriate reward functions, like whether it's a model, whether it's a hand-coded functions, but we do require that in order to make it work.
Any questions? Any other questions? So I have a few questions. Oh, you mentioned AI agents that can perform end-to-end tasks, and I'm curious, what do you think about ensuring safety on a physical level? For example, obstacle avoidance, respecting physical limits.
Yeah, this is something that I'm like very curious about, but I do not have the expertise in that field. But I'm very curious how can we ensure the safety there, because once we apply the foundation models in physical worlds, it will cause like severe like consequences if it's not safe. So yeah, I'm happy to chat more about how to ensure safety. Yeah.
And another question I have is, do you think the probabilistic perspective could be used to ensure safety in combination with word models? Because we can use word models to represent the state transition function for the dynamics of the system, right? So I don't know if you are aware of any existing works in that direction.
I don't think there are such works because this probabilistic perspective is still quite new. And I also don't think word model is safe enough. It's my guess is that
there's no safety guarantee mechanism.
Yeah, exactly. Yeah. And my feeling is that it's pretty vulnerable. Yeah.
Awesome. I'd be happy to look at more.
Thank you. Yeah.
Any other questions from the audience? Yep.
For the mirror paper, I wonder how to calculate the prior. It seems it's very hard to calculate the prior, to have an accurate prior.
So actually it's quite easy because the prior is just the base model, the attack. So basically we have an attacker model at the beginning and then we update model, right? The original attacker model serves as the prior and the updated model serves as the Q distribution, the approximated positive distribution. So you can just compute the output distribution based on the original attacker model. Yeah, so we have the prior bit of.
Yeah, so you mean the token level output distribution on each token
Yes,
of the
yes, exactly.
original attack
Yes.
model.
Yes, and equitably, the prior serves as the role to ensure that the outputs, like the fine-tuning the model are not too far away from the original model, because we know the original model is already pretty good. It kind of outputs like fluent text. So we do not want the fine-tuned model to be too far away from it because we want to keep its original capability. So that's kind of the equivalent role of prior.
Maybe last question.
Yeah, just curious about your first part of the book. You mentioned when you're shifting from text language model to visual language model, there's a complex interaction between language and image. What is the trick to handle this kind of complicated interaction? It is just more data, or we need some architecture change?
Well, actually, we didn't do much to enforce that. We still use the attacker LM to handle that interaction. Like we just tell the model, hey, this is the target output we want. Can you generate a pair of text and image? Yeah, to satisfy that. So yeah, it's again like depends on the capability of the attacker models.
Thank you.
Yeah. Thank you for the fantastic.
Thank you very much.
Thanks.